Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this series on the modeling of multiphysics system. So this is the third lecture in the segment of coupled physics in which we are coupling two or more physics together and trying to get a sense of how we can model the system. The variables will be dependent on each other. Say right now we are going through thermo-mechanical systems or thermoelastic systems in which there is a heat input and the temperature variation or the thermal energy is causing a mechanical response or a mechanical output. So in the former two lectures, we have looked at different devices and actuators which work on this principle, and we have mostly done the modeling for the thermo-pneumatic devices. So what is thermo-pneumatic device is that you have a heat input from a heat source, primarily from a resistive heater, and that resistive heater is causing or transferring heat to a gas. The gas is expanding, and due to the expansion of the gas, we have either a spring piston system or a membrane, any of which due to the expansion of the gas, due to increase in pressure, that membrane would move or the piston would move and cause some form of a deformation. Thermo-pneumatic devices are very well used in the case of say a peristaltic pump or some actuation device wherein you can give a small electrical input. That electrical input causes heat generation, making the gas expand and causing some deformation or some deflection. Okay, but these systems are again there is an intermediate species, that is a gas which is expanding due to an increase in temperature, keeping the pressure constant, and that gas is in turn giving a load to a membrane or to a plate that is deforming, and so there is an intermediate case. In this lecture, and this is the third and the last lecture for this set of thermomechanical systems, we will cover up the linear thermoelasticity, the concepts of heat directly causing displacement or strain. That is the concept of thermoelasticity. So this we very well know that if we have a body and we heat up this body, then the body would expand, and when we cool it down, then the body would contract. Now, if the body is naturally placed say on my hand and I heat this up, there will be no stress state in the body because the stress is the resistance to some deformation. Now, if I am not giving any resistance, it is just free floating on my hand and there is no friction, then the body can expand and contract and there will be no stress state, or there will be strain and there will be deformation, but there will be no stress in the body. However, now if I hold the body from two ends and I prevent it from expanding and then I give it a temperature increase, a uniform temperature increase, then this body will bend. Likewise, you can have the same thing that if I have an unconstrained body, but there is a thermal gradient within the body, that means temperature is not uniform and it is high at one end and low at another end. In that case, we will again have a strain and a stress in the body. The region which is hotter will want to expand more, the region which is colder will not want to expand as much. Right. So, the colder region will pull onto the hotter region and will cause some form of compression. The hotter region will push into the colder region and that will cause some form of tension. Right. So, we will have a set of tension and compression on the body, and that is the case of thermoelasticity. So, the first thing to look for is the heat transfer equation. So, the thermal model that we have studied earlier was driven by the Fourier's law, and the heat diffusion equation is modified by a heat source from the heat released due to dissipation of strain energy. Okay. So, our thermal model was rho Cp del T by del T was equals to del dot K del T plus Q dot. So, we had this energy storage term we have this thermal diffusion term, and then we have this heat source, and this heat source is where we can modify, and this will be equals to, this heat source will be minus alpha 3 lambda plus 2 mu T0 del epsilon kk by del T. So, this is our strain rate, or the rate of change of strain with time. Epsilon kk is on the principal axis, summation of the principal axis. So, if you take the summation of the diagonals or the trace of a matrix, in short, that will be epsilon kk, epsilon 1 1 plus epsilon 2 2 plus epsilon 3 3. If you have a time derivative that the strain is changing with time, then that adds up to the heat stored, and these are a set of constants where if you remember when we were doing heat transfer, and if you go back several lectures, the heat transfer we had an alpha term that was the thermal diffusivity, that is K over rho Cp. K is the thermal conductivity, rho is the density, Cp is the specific heat. Alpha in this case is the thermal expansion coefficient. That is how much the body is going to expand due to a temperature rise, right. So, alpha L delta T will be the net strain in a body, or net displacement, alpha delta T will be the strain, how much the body is going to rise or deform due to a temperature variation. Okay, so, this additional term is what we are getting due to thermal dissipations from strain rate or from the strain variations of the body. Likewise, we can develop a similar model for our, so this is our thermal model. Then our mechanical model is also driven by temperature. Whether the temperature difference in a body, the stress tensor, that is a Cauchy stress tensor sigma ij, if we can rewrite that again, was E over 1 plus nu epsilon ij plus E nu over 1 plus nu 1 minus 2 nu delta ij epsilon kk minus E alpha delta T over 1 minus 2 nu del ij. Okay. So, what we have is we are using a small strain model where epsilon ij is an infinitesimal strain tensor, that is del ui by del xj plus del uj by del xi, and we are using an isotropic material. For a cubic isotropic material, this is our stress strain relation between sigma and epsilon. We have this additional term, and that is due to the temperature gradient or the temperature difference induced strain or stress effects, right. So, with this we can then develop our mechanical model around a temperature gradient or temperature difference from our conservation of linear momentum. We have del sigma ij by del xj plus rho bi equals to rho del square ui by del t square. So, so this is our conservation of linear momentum. If you would like to have a more in-depth understanding, we have covered the mechanical model and all aspects of mechanics in about a 6 lecture set. If you go back within this lecture series, when we were doing single physics, we have covered each of these single physics, and that is the reason to do individual physics, is that we have an understanding of the models before we can couple them together. Alright, so if you go back to the set of notes for solid mechanics, you could there find the mechanical model, and from the mechanical model now we are trying to incorporate the thermal aspects into the equation. So, we need to find this del sigma ij by del xj, that is divergence of the Cauchy tensor. So, del sigma ij by del xj is equals to, if I see what it is E over 1 plus nu epsilon ij. So, del by del xj of E over 1 plus nu epsilon ij plus E nu over 1 plus nu 1 minus 2 nu of epsilon k k del ij minus this del by del xj of E alpha delta t over 1 minus 2 nu to del ij. Alright, that makes sense. Now, we can introduce certain constants. So, E and nu are one set of constants. These are called our material properties. E is the elastic modulus, nu is the Poisson's ratio. A combination of E and nu can also be written in terms of Lamé constants. There are two Lamé constants. One is the shear modulus. Shear modulus is defined as E over 2 1 plus nu, and the Lamé modulus lambda is equals to E nu over 1 plus nu 1 minus 2 nu. Okay. If we take 3 lambda plus 2 mu, you will find out this will come out to be, if we can put it up over here, we will find out this comes out to be E over 1 minus 2 nu. Okay. So, we can see that some of the terms are defined over here. Therefore, sigma ij, let us first write sigma ij in terms of these constants. This was 2 times mu of epsilon ij plus lambda of epsilon k k del ij minus alpha 3 lambda plus 2 mu delta t del ij. Okay. Now, let us take the derivative. Del sigma ij by del xj is equals to 2 mu del epsilon ij by del xj plus lambda del epsilon k k by del xj delta ij minus alpha 3 lambda plus 2 mu del t by del xj delta ij. Okay. Now, we have defined what epsilons are. Epsilon is 1 by 2 del ui by del xj del uj by del xi, where u is the displacement. So, this we can rewrite as 2 times mu into 1 by 2 of del square, and we are differentiating with respect to j, del square ui by del xj just del square uj by del xi del xj plus lambda of del square u k del xk delta ij minus alpha 3 lambda plus 2 mu del t by del xj delta ij. Okay. So, this is our entire expression. It looks very messy. Let us clean it up a bit. These two will get cancelled away. So, the first term becomes mu del square ui by del xj plus del square uj by del xi del xj plus lambda. Now, there is a property of the Kroneker's delta, which suggests that if del ij is there and we have this j as a repeating index, we can replace j by I. Again, 2 repeating index k we can replace by any alphabet. So, it can be very well be j. So, this is del square uj by del xi del xj. J is repeating, those get cancelled away, I is remaining because j and I we have replaced, minus alpha 3 lambda plus 2 mu. We can do the similar treatment, again j is repeating, we can write this as del xi. That is the property of the Kroneker's delta. Again, these properties we have discussed in depth in the initial set of lectures. The first 5 lectures we have gone over vector calculus and the index notation and how these define. Okay. Now, let us club up some terms together. So, we can say in short that del sigma ij by del xj plus rho bi equals to rho del square ui by del t square can be written as, now we can club this this term with this term, which will have mu plus lambda del square uj by del xi del xj plus mu of del square ui del xj del xj minus alpha 3 lambda plus 2 mu del t by del xi plus rho bi equals to rho del square ui by del t square. That is a final expression that we get. So, lambda plus mu del square uj by del xi del xj, that is your first term. That is uj changing, so you are adding over del square u1 by del x1 plus del square u2 by del x1 del x2 plus del square u3 by del x1 del x3. So, j is repeated, so you will add over j. This is just a brief catch up of what was index notation. Again, please go back to the lectures and see what index notation was. Then the second term is just based upon mu. Third term is where our temperature dependence is coming. Then we have our body force term, and finally we have our acceleration term. So, we can see that this expression finally is our final expression for our solid mechanics model. Okay, so we have two equations now. The first equation was this with our heat source, and the second equation is this which has our temperature gradient term. So, we have a thermal model dependent upon strain in terms dependent upon displacement, and we have a displacement model which depends upon temperature. Now, let us see if we can apply this to the thermal expansion of a rod. That is a one dimensional problem. So, consider a 1D rod that is fixed at one end and free on the other. Alright, so we have a rod that is fixed on one end and that is free on the other end. This is x is equals to 0. Let us take this direction as x1, this as x2. In this case, it is one dimension, so the variations are only in x1. In that case, u1 is only a function of x1. We consider a steady state analysis. We consider a steady state model for this. We will come to the temperature part later. Let us first do the mechanics part. So, let us write our equation again. So, we had rho del square ui by del t square was equals to mu plus lambda del square uj by del xi del xj plus mu del square ui by del xj del xj minus alpha 3 lambda plus 2 mu del t by del xi plus rho bi. Okay. Now, I is equals to 1. We are only concerned about the movement along x1. We see that u1 is only a function of x1. It is steady state. So, the first term becomes 0. Then you have mu plus lambda. Let us expand this. This will be del square u1 by del x1 square plus del square u2 by del x1 del x2 plus del square u3 by del x1 del x3. I is 1, j will be added over plus mu del square u1 by del x1 square del square u1 by del x2 square del square u1 by del x3 square minus alpha 3 lambda plus 2 mu del t by del x1 plus rho b1. Okay, this is our expression. Now, let us get rid of some terms. u2 and u3 are 0. u1 is only a function of x1. So, derivatives with respect to x2 and x3 will be 0. There is no body force in this case, we are ignoring the effects of gravity. So, we can neglect this body force term and equals to 0. So, what we get if we bring this together, it will be lambda plus 2 mu of del square u1 by del x1 square is equals to alpha 3 lambda plus 2 mu del t by del x1. So, this becomes our mechanics model. We also have a thermal model. So, the thermal model we will have likewise rho Cp del T by del T is equals, let us take the thermal conductivity out, and K del square T by del x1 square plus del square T by del x2 square plus del square T by del x3 square plus Q dot. Now, again temperature is only a function of x1. In that case, the time derivative is 0, x2's variations and x3 variations are 0, and we can write rho Cp del T by del T is equals to K del square T by del x1 square plus Q dot. Oh, and the first term is also 0, its time variation is 0. Okay. So, we now have two equations. One is our equation with respect to position as a function of temperature. Second, we have an equation of temperature. We have not added a function of position in Q dot as of yet. Now, there are certain things that we can do. We can assume the body has a temperature variation or temperature gradient. So, let us take this rod and take a simple case. Let us again take this rod. Assume that there is no heat variation in this case. Q dot equals to 0. So, the left side has a temperature of T hot, right side has a temperature of T cold or Tc. That means that there is a linear temperature variation through this. So, we have two boundary conditions to solve this. So, solving the thermal problem, we will have K d square T by dx1 square equals to 0, which gives dt by dx equals to C1 and T is equals to C1x plus C2. Now, with these boundary conditions, if we put at x is equals to 0 is equals to C2 and that is equals to T hot, and T at x is equals to, say this length is L, this is 0, then at T at L is C1L plus T hot is equals to T cold. Therefore, C1 is equals to Tc minus Th over L. Therefore, our temperature equation T of x1 will be equals to T hot minus T cold over L into x1. All right, this is the variation of x1. So, this becomes our temperature equation. It is a linear variation with temperature. On the left hand side it is T hot, on the right hand side it is T cold. If you put the value of x1 as L, it will come out to be Tc. Okay. Then solving for the mechanics problem. Okay. Our equation, if you go back one slide, was del squared u1 by del x1 square is equals to 3 lambda alpha times 3 lambda plus 2 mu over lambda plus mu 2 mu of del t by del x1. Now, in this case temperature is not a function of time, it is just a function of x1. You can write this very well as dt by dx1. As of now, let us assume that we do not know that function of temperature. We take it as is and later on we can put that value. We will need two boundary conditions. We will say that at u at 0 or u1 at x1 equals to 0, it is fixed at this end, that is 0, and du1 by dx1 at x1 equals to L is equals to 0. That is, it is a free end, so that the free end the slope is 0. At the fixed end, we have the displacement as 0. Okay, very well. Now, if we can integrate this once, we will get du1 by dx1 is equals to alpha 3 lambda plus 2 mu over lambda plus 2 mu of temperature plus a constant C1. If we integrate it again, then we will find u1 as a function of x1 as alpha 3 lambda plus 2 mu over lambda plus 2 mu, integration from 0 to x1 t as a function of z, and let's say it's a time driven function as well, dz plus c1 x1 plus c2. Okay. Now we have two constants to solve for. First, let's put u1 for x1 equals to 0. u1 is equals to, this term becomes 0 because the integration is between 0 to 0. c1 term becomes 0 plus c2, that is equals to 0. At x1 equals to L, du1 by dx1 at L is equals to alpha 3 lambda plus 2 mu over lambda plus 2 mu t at L, and t at L we have defined as t cold. So, we can write this as t cold. Alright, this is the value plus C1 is equals to 0. So, C1 minus alpha 3 lambda plus 2 mu lambda plus 2 mu of Tc. Okay. We can then substitute it back into our equation, and then u1 of x will come out to be alpha 3 lambda plus 2 mu over lambda plus 2 mu. This term you can take it out as common. We can have an integration from 0 to x1 t1 or t at z comma t dz minus tc. Okay. So, this looks something like a delta t, which is t if you integrate over z into x1. So, I forgot, okay, because it is c1 x1. Okay. Now, this is our expression for our u. So, we have now an expression for temperature as a function of position. We have an expression for displacement as a function of position. So, we have solved this coupled equation. We have decoupled. It was halfway coupled. It was only one way coupled. It was not two way coupled. And we have solved this. Temperature, we can now put T over here, which is a linear variation, and we can integrate into this. All right. Now, let us take some special cases. This term 3 lambda plus 2 mu over lambda plus 2 mu, this term it comes out to be equals to 1 plus nu over 1 minus nu. And for the limiting case of nu tending to 0 of 3 lambda plus 2 mu over lambda plus 2 mu, this term is equals to 1. Okay. This term is equals to 1, that is for very small values of mu, we can take this. Also, let us consider that Tz comma T is a constant at a given temperature T. Okay. So, let us take this as a constant. So, these are some more approximations we are taking. Now, we have solved the full equation, we can assume some approximations. Let us say that the body is uniformly heated up, the temperature is constant throughout. Also, our Poisson's ratio is tending to 0. That means that the deflections are only along the x1 directions, and there is no lateral deflections or no lateral strains along the y and z direction. So, if that is the case, then our equation of u1 of x will boil down to be alpha of T of x1 minus Tc of x1 is alpha x1 T minus Tc. Okay, this looks very similar to our displacement equation for strain. u1 of L will be equals to alpha L T minus Tc, which is alpha L delta T. This we know very well. Our strain, that is del u1 by del x1 will be equals to alpha T minus Tc, that is alpha delta T, that is our strain. Our new length of the rod after heating to a certain temperature L nu will be equals to L plus u1 of L, and that will be equals to L 1 plus alpha delta T. That is the final length of the rod. Okay. So, that makes sense that we have considered a system in which the temperature was varying with position, and we had a system which was free at one end and fixed at another end, and we saw how the variations of displacement happen due to this temperature gradient. And then we took a simple case in which the temperature is uniformly varying, and we found out that these relations is something that we know very well from our understanding of solid mechanics, that the strain in a body due to a temperature rise or uniform temperature rise is alpha delta T, equivalent displacement is alpha L delta T, and then the new length of the body is L1 plus alpha delta T. And the stress in this case sigma 1 1, will be the stress sigma 1 along the principal direction will be equals to E alpha delta T. That is your strain. This is epsilon 1 right. But this is a very special case of a one dimension expansion. We have taken the Poisson's ratio to be tending to 0, and then this is the case. For a more general case, then we will take this set of solution where u1 of x is alpha 3 lambda plus 2 mu over lambda plus 2 mu integration of T dz minus Tc into x1. All right. So, this is for a linear system. It see that the temperature change or a thermal response is causing a direct mechanical response. So, any say you are using an electrical heater, and this is a metal rod on which you are passing current through. This is causing heat generation. That heating is causing this rod to expand. That is a direct mechanical output from a temperature variation within the body. The stresses generated in the body is due to the thermal gradient or the del T by del X. Now, what will happen if there is no temperature variation or temperature gradient? If there is uniform temperature, in this case we will still get a new rod length, we will still get some strain in the body alpha delta T. However, if you look at this stress term, and this stress term over here, sigma ij or del sigma ij by del effect of the stress term in the Navier's equation is dependent upon del T by del xi, and that del T by del xi, if the temperature is uniform, will be 0. In that case, the stress effects in the conservation of linear momentum is 0. All right. Now, we look for the next case, and that is for a modeling of a V-beam actuator. So, a V-beam actuator is a device which is pinned at the two ends. It's a beam. So, a beam that is supported at the two ends. Now, we can pin this, we can fix this. It's a beam. That means that the second dimension is important and it has a deflection component present. And if there is a temperature variation within this, it's likely to deform as such. Okay, if it is expanding and if you have fixed these two ends and the temperature expands, it's likely to bend. Right. So, that is a V-beam actuator. The equation for a steady state V-beam actuator is d square dx square into EI, that is a rigidity modulus, d square V. The V is a deflection in the y direction by dx x square plus P d square V by dx square equals to F, where V is the displacement in x2 direction. This is x2 direction, this is x1 direction. X is actually x1 direction in this case. Okay, x2 or y direction. Okay. Now, this is a slight modification from our linear system. We have this additional term that is due to the bending effect apart from the stretching effect. P was initially we had a minus mu term. If you took it to the F to the right hand side, that minus mu term is due to the pre-tension in the body. The tension can be replaced by a plus P term, and that is a pressure force. So, this is a pressure force or the inherent pressure. Say I have compressed this and I have pinned it together. Then in that internal pressure or the inherent pressure is this pressure force. The F is an external force, and this is defined as P of x minus d square the moment due to the temperature by dx square. Now, you would ask that what happened to this thermal gradient term. If you go back and we see that the thermal gradient as over here is along the direction of the displacement. So, the displacement is along y direction, the thermal gradient will also be along y direction, right. So, if the thermal gradient see dt by dx1. So, if the thermal gradient is along y direction, in this case the temperature difference is along x, not along y, right. You are expanding in x, you have a thermal gradient in x, and that is causing the beam to deflect. So, what is the effect of temperature? That it is not allowed to expand, it is pinned at the two ends. It is not allowed to expand, that is why it is creating a moment due to this force of expansion, and that moment is causing it to rotate, and this effect of the moment is given over here. So, this P is applied load not including thermal stress and this is the moment due to thermal expansion, or rather restricted thermal expansion. Okay, so we have a constrained or a restricted thermal expansion, and that is causing this moment. This mtz, okay, now this px can be any force. It can be gravitational force, it can be some electromagnetic force, but not thermal stresses. That's what I want to convey. So mtz is equals to integration over the cross section of alpha e t into y into dA. Okay, alpha is the expansion coefficient, E is the elastic modulus, T is the temperature, and Y is the y direction, that is x2 direction, dA is the cross section area. The integration over the cross section, in this case it is the x2 x3 plane or the yz plane. Okay, you can get used to either using x1, x2, x3 or yz. I am trying to use both so that you can have an understanding of how these two are related. And the coordinate systems you can number 1, 2, 3 or x, y, z. Okay, likewise mty, so moment due to temperature variations along the y direction is equals to alpha e tz d. Okay, the same formulation, just y is replaced by z. Now, let us assume that the temperature variations and the moments are 0. Let us say that the applied pressure term is also 0. Then this equation can be simplified. So, now consider the case where the moment is 0. So, in this case and our external load force is also 0, which gives that force term or the forcing term as 0. So, our equation it becomes EI d4v by dx4 plus p d square v by dx square equals to 0, or d4v by dx4 plus k square d square v by dx square is equals to 0. Okay, where k square is equals to p over ei. All right. So, this equation we can solve. We need 4 boundary conditions. So, 2 on the left, 2 on the right. So, boundary conditions will be that v at 0 and v at L are 0, d square v by dx square at 0 and d square v by dx square at L are also 0. So, that is the case of a simply supported or a pinned system, not a fixed system. If it is fixed, then there will be other boundary conditions. Again, if you go back to the set of lectures on solid mechanics, we have done beam modeling in depth. From there you can see what simply supported boundary conditions are, what fixed boundary conditions are, and so on. Okay. Now, if we solve this differential equation, we will find out that v of x is equals to a naught plus a1x plus a2 cos of kx plus a3 sin of kx, right. Again, at x is equals to 0, we will get v of 0 is equals to 0, that is a naught plus a2, and d square v by dx square of 0 is equals to 0, that is a naught minus a2, which implies that a naught equals to a2 equals to 0. Okay, so the 2 terms are gone. Remaining 2 terms, we will do it at x is equals to L. We will have one thing is a1 will be equals to 0. So, if you take the second derivative, you will find out that the a1 term is gone. So, the first derivative, I am sorry. So, the if we do this d square v by dx square of x, that is, so this term goes away, this term goes away, we will have minus a3 k square sin kx. automatically the A1 term goes away. So, the A1 term is 0. So, we will put x as L over here. Now, the next thing is d square V by dx square. This is one case, right. Another case is V of L, that is equals to A1L, A naught is 0, A1L plus A3 sin KL. This one, if you put x is equals to L, this will be minus A3 K square sin KL. I am just going to show you how this come up. Okay, now both of them are 0. To have both of them 0, first of all A1 needs to be 0 because A1 is multiplied with L. So, that is why A1 is 0. Then the next thing is either A3 is 0 or sin KL term is 0, otherwise this equation cannot be 0. So, individual elements need to be 0. Therefore, if I just take this away, so either A3 equals to 0 or sin of KL equals to 0. Now, if A3 is 0, then solution becomes trivial or redundant. That means that everything is 0, A naught, A1, A2, A3, all of them are 0, and that means that u of x is 0. There is no displacement. That is not a solution. Now, the another case is that sin KL is 0, and this gives us a set of eigenvalues where k of L will be equals to n pi or kn equals to n pi over L, where n belongs to 1, 2, 3 and so on. Okay, that is your k of n. Therefore, if we write it quickly over here, our v of x therefore will be equals to, now what we have is only A3 and n. So, v of x will be equals to A3 over L. Our critical load Kn, which is n pi over L, is also equals to P over Ei. For n is equals to 1, that is the first oscillation node, our P critical will be equals to pi Ei over L. Again k square, Kn is this, k square, square of this, pi square Ei over L square. So, this mode of oscillation is called the Euler oscillation or the Euler vibration. Of beam buckling. All right. Now, we will consider the case where the thermal variations exist. So, we are taking the case of a thermal bimorph actuator. So, thermal bimorph actuator, it will look something like this. We have the same material, we have two arms, one arm is thin, one arm is thick. We have a temperature rise, a uniform temperature rise, and the temperature rise, the thinner arm would like to, we have a temperature difference. So, this will be at T8, thicker arm will be colder. Due to the temperature difference between the two arms, the actuator will deflect, and then once the arms are again back to the same temperature, the temperature has diffused through, then the actuator will come back to the original state. And in this way, you can control the motion of an actuator. Now, this actuator is again a beam. So, instead of modeling two arms, again the principle is to create a thermal gradient between two arms of unequal length. Okay. Now, instead of modeling this structure you can model with a finite element analysis. You can put in a temperature effect through this. You're solving the thermal model. You can also put in this our mechanics model. Typically done through FEM. You can take any FEM software. You can put in this design, this model, and you can simulate. But to simplify, to do an analytical understanding, we simplify this by a single beam, so single cantilever beam, that is fixed at one end and free at another end. That is the definition of a cantilever beam. and we say that the temperature variation T along y direction is equals to Th minus Tc over H into y plus Th plus Tc all by 2. So, let us write design this system. So, let us take that this is the beam. Okay. Again, let us mark our direction. This is x direction, this is y direction, this is z direction. From the center of the rod we are taking, or center of the beam we are taking this. Now, the lower plate is at a temperature Tc, the top plate is at a temperature Th. Let us take the height as h, let us take the width as w. Okay. So, this is from our thermal model. I am not solving thermal model again, we have done this before for a temperature variation, a linear temperature variation with no heat generation, we have solved this before. We will do the mechanics model for this. So, we will have EI d4V by dx4 plus P d square V by dx square is equals to F, where F is equals to P of x minus d square m T z by dx square. Again, Px is the applied load without the thermal stress effect, and d square T m T z by dx square is the effect of stress or the forces due to moment variation. All right. Now, we can find out m T z is equals to integration over area A alpha E T into y into dA. What is dA? dA is dy dz, and the integration is over the yz plane. The area is w into h. Again, temp T is a variation along y. So, we can integrate this and we will find out again integrating with respect to y and h, E of this Th minus Tc by h into y plus Th plus Tc by 2 into y into dy dz. So, if you integrate this, you will find out that mTz will be alpha E W h square over 12 Th minus Tc. Alright. So, this is our alpha value. Likewise, you could find for mty. Now, d square mtz by dx square is 0. We can see that temperature has no x variation, although the integration is along y and z, we have integrated that, there is no x variation. In that case, d squared mtz by dx square term is 0. Therefore, our f is only px, and let us take that there is no external load. So, our equation again boils down to EI or d4v by dx square. Let us take it equals to 0 and say that the p term is 0, that is no pretension in the body. As a free cantilever beam, there is no pretension, it is not preloaded from the two ends, d4v is equals to 0. Where will this temperature effect come? Now, you would assume is dx4. So, this becomes our governing equation. We look for the boundary conditions. So, on the left end it is fixed. For a fixed end, x is equals to 0 is fixed. So, v of 0 d by dx of v of 0 is equals to 0. For the free end, x is equals to a, that is a free end, we will have EI d square v by dx square of L, that is equals to the moment causing it to bend, and EI d cube v by dx cube of L plus p dv by dx, so minus m dm tz by dx. Okay. So, these are the 4 boundary conditions that we are solving for. Now, in this boundary condition, we can see that the p term is 0, the mtz term is 0. So, we can say that d cube v by dx cube of L is equals to 0. mtz we do have a value, so we will need to find that out. Okay, so with this, we can then write this term out as EI d squared v by dx square of L, so minus MTZ we have just found out is minus alpha EW h square by 12 TH minus TC. Okay, now this is our expression to solve for. Oh, I'm sorry, I have a minus over here and this should be plus. Okay. Now so this is one boundary condition and this is a second boundary condition, and then we have two more over here. So we will solve with this. We will find out that v of x, so solving the governing equation, we will find v of x will boil down to minus wh square alpha over 24 into I th minus tc into x square. So this becomes our equation. You have put in the four governing equations, four boundary conditions into our governing equation. Governing equation will be again will be c1 x cube plus c. So if we integrate this, d cube v by dx cube will be c1. Integrate again, d square v by dx square equals to c1x plus c2. Integrate again, dv by dx c1x square by 2 plus c2x plus c3. Integrate one more time, we will have c1x cube by 6 plus c2x square by 2 c3x plus c4. We will have four integration constants. With the boundary conditions, if we put into here, we will get all the four integration constants. Our equation boils down to this. Now we can then find out what is the moment of inertia. The moment of inertia I is integration of y square over a into dA. Again, this is the yz plane. If we substitute what we find from the moment of inertia, so substitute I in v of x, we will get v of x v minus alpha th minus tc over 2 to x square over h. So it's a much simpler formula to handle. The maximum deflection is v of L is at the free end, v of L is minus alpha th minus tc over 2 into L square over h. Okay. So what we have done for a bimetallic strip, actuated to a bimetallic strip, in this case they will have two different expansion coefficients. You can solve a similar linear thermoelastic model and with two different alpha values and get the solution of that. And now what we have done, just to summarize everything together, is we have a body that is expanding due to a temperature difference. That expansion, if it is constrained or there is thermal gradient, will cause stress in the body. And so we have coupled a thermal model which is giving a temperature profile to a mechanics model which either is expanding and you are getting the expansion, or is pinned and it is getting deflected due to a moment. And we have seen how these equations can be solved. Numerical analysis of this can also be done. It is very similar to our thermopneumatic systems. You discretize them in space and time, and then you can put in the boundary conditions and you try to solve them. So thank you for listening to this lecture, and in the next lecture we will start with the effect of electricity on mechanical system, that is an electromechanical system. So thank you so much for listening.